So now we start lecture number 7 of the course Engineering Mechanics. In this lecture, we are going to derive two very important relationships. These two relationships are called the velocity transfer relationship and the acceleration transfer relationships. The context of these relationships is the diagram that I have shown on the right hand side of the screen. As usual, we have two reference frames. The first reference frame is F and the second reference frame is M. There is a particle P which is freely moving in space. Our primary objective here is to find velocity of this freely moving particle P with respect to the frame F. The expression for VPF will be obtained by using the frame M as an intermediate frame. By intermediate frame, by the phrase intermediate frame, I mean that I would like to write the expression of VPF using the quantity VPM. So the importance of intermediate frame here is that somehow we know the velocity of the same particle P with respect to the intermediate frame M, and we want to transfer that information to enable us to find or ascertain the velocity of the same particle with respect to F. Now this relationship between VPF on one side and VPM on other side, it involves few more quantities. One quantity is the angular velocity of frame M with respect to F. It also involves the position vector of P measured from a point which is fixed in M. In this diagram, that point is A. So there is a point A which is fixed in M, and we are utilizing that to find VPF. Just like we call the frame M as intermediate frame, we would like to call this point A as the intermediate point. So now we have an intermediate frame and an intermediate point. Note that this relationship requires identification of an intermediate point, and that intermediate point must be fixed in the frame M. Otherwise, this relationship will not hold good. When I derive this relationship on my next slides, we will see why exactly this condition is required, that A must be a point fixed in the intermediate frame. So now with this intermediate point A, we are measuring the position vector of P from A, and that position vector appears in this cross product. Then there is one more information required to complete this relationship, and that information is about the velocity of the same intermediate point A with respect to frame F. That's the third term. So with these three pieces of information on the right hand side, we can write the complete expression for VPF. So this is the velocity transfer relationship. The other relationship of interest in today's class is what we call the acceleration transfer relationship, and I have written that relationship also on this slide. So the main focus, the primary quantity of interest as far as the acceleration transfer relationship is concerned is the quantity APF, acceleration of particle with respect to frame F. On the right hand side of this relationship, we have five terms. Five terms are there. If I start from the rightmost term, I have the information about the acceleration of the same particle P with respect to M. This is similar to what we had in the velocity transfer relationship. On left hand side I had VPF and on the right hand side I had VPM. So the transfer is happening from VPM to VPF. Likewise, in the acceleration transfer relationship, one may view the relationship as the information about APM being transferred to eventually arrive at the value of APF. The second term from the right in this acceleration transfer relationship is a cross product which involves the angular velocity of M with respect to F crossed with VPM. This VPM is the same quantity which appears here, acceleration of particle P with respect to the frame M. The third term on the right hand side of this equation is a double cross product, and this double cross product involves the angular velocity of M with respect to F, and it also involves the position vector of P measured from A, and this A is the same particle which was appearing in the velocity transfer relationship as well. I repeat, A must be a point fixed in M, must follow this condition. The fourth term on the right hand side involves the angular acceleration of frame M with respect to F crossed with the position vector of P measured from A. Finally, the fifth term on the right hand side is the acceleration of point A with respect to F. So there is a correspondence between VAF term that was appearing in the velocity transfer relationship and the AAF term that is appearing in the acceleration transfer relationship. Now let us try to derive these two relationships. How do we get these mathematical forms? Before I start the derivation, I do want to mention that this term 2 times omega mf cross VPM is also called the Coriolis acceleration term. proof of velocity transfer relationship. We will refer to this diagram on the right hand side of the slide. It is essentially the same diagram what I had earlier, even though the orientation of the two frames on the diagram looks somewhat different. Conceptually, the context is the same. I have a frame F, another frame M. A is a point that is fixed to M, and then P is that free particle, and then I have drawn three position vectors of P. One measured from point O, that vector position vector is RPO, where O is fixed in F. Another position vector is RPA, and the third position vector is RAO. We will see the significance of these vectors in our derivation. So to derive the velocity transfer relationship, I start with the definition, with the very definition of VPF, which is written here. It is the rate of change of the position vector of P with respect to F, where the position vector is being measured from a point O which has to be fixed in F. This is the very definition of VPF. Now looking at the diagram on the right hand side, we can express RPO using the two vectors RAO and RPA that are displayed on the screen here. I substitute this expression in RPO and this is what I get. So now the time derivative operator has to act on two terms, these two, the sum of these two terms. These are the two derivatives with respect to F. Thus, VPF should be the sum of these two terms that we have marked here. When we observe this term, the first term, we find that d dt of RAF is nothing but VAF, the velocity of point A with respect to F. Point A is fixed to M, nonetheless it will have some velocity with respect to F, and that's what this term is. The second term involves time derivative of RPA with respect to F. We want to process this further, this term, the second term. I call this equation as 1 and I keep it in reserve for the time being. At this point, I would like to recall the useful relationship relating the rate of change of any vector with respect to F and with respect to M with this extra term. In the last class, we used this particular equation to find a relationship between angular velocity, between the angular velocities of three different reference frames. Further, we also use the same relationship to derive a useful relationship between the angular accelerations of three different reference frames in context. Yet again, I am calling this relationship in the context of velocity transfer relationship as well. This equation, as we know, is true for all vectors. Thus, I am free to set this vector A to RPA for my application right now. Once I set A to be RPA, I get this relationship, what I am highlighting here. I get d dt of RPAF, d dt of RPAM, which comes from here, omega mf cross RPA. Once I have d dt of RPAM, and given the fact that A is a point fixed in M, we can replace this by the physically sensible quantity Vpm itself. This time derivative is nothing but the velocity of particle P with respect to M. Indeed, this is the step for which we took A to be a point fixed on M. While commenting on the contents of the previous slide, I did mention that both the velocity transfer relationship and the acceleration transfer relationship use an intermediate point A, which has to be fixed in the intermediate frame F. And you see the importance of this when I replace this expression by Vpm itself. And then this term just remains unchanged. I call this equation number 3. This I called equation number 2. So what should be our next step? Our next step should be to take this expression for d dt of RPA with respect to F and put it here, back in here in equation number 1. That's what I'm going to do now on the next slide. Rather, I have it here itself on the right hand side. So here I have written substitute the relevant quantity, which is this. Substitute this quantity from 3 into 1 and you arrive at Vpf equals VAF, which comes directly from here, and this quantity gives me these two terms which I just derived in 3 here. So I get omega mf cross RPA plus Vpm. This is exactly what I presented on the previous slide as the velocity transfer relationship. This completes the proof. The next item we want to take up is the acceleration transfer relationship, the proof of the acceleration transfer relationship. We start the proof with the same context, same two reference frames, freely moving particle P, frame M, frame F, O fixed in M, A fixed in O fixed in F, A fixed in M. The first step is to write APF as the time derivative of VPF, and also we remind ourselves that APM will be d dt of Vpm with respect to M. Wherever required, I would like to make these substitutions. But for the time being, let's focus on APF, which I wrote like this. And now this VPF I'm going to replace by my already proven expression for VPF, that is the velocity transfer relationship. So VPF is being replaced with the three terms VAF, VPF plus omega mf cross RPA, the relationship I derived on the previous slide. Now we allow this derivative operator with respect to f to distribute itself over the three individual terms here, and this is what we get. I call this equation 1. Now the first term which is appearing here, d dt of VAF with respect to f, is nothing but AAF. In the acceleration transfer relationship, indeed this term appears. So we have claimed the appearance of this term in the final form of the acceleration transfer relationship. The next step is to again recall this useful relationship for the rate of change of f observed from two different reference frames, and I am going to set this time, I am going to set A as VPM. When I do that, I am able to write rate of change of VPM with respect to f as sum of two terms, rate of change of VPM with respect to m and omega mf cross VPM. Why am I doing it? I am doing it because back in 1, the second term is indeed the rate of change of VPM with respect to f. And here I have been able to express this as the sum of these two terms. Now this term that we have, this is nothing but APM, acceleration of P with respect to M. That is what I wrote earlier here also. So I have rate of change of VPM with respect to F is APM plus omega MF cross VPM. I keep this as equation number 3. This was 2. Now I am going to focus on this term back in 1. That term is rate of change of omega MF cross RPA with respect to F. Applying product rule of differentiation, I write this term as sum of these two terms. One term involves rate of change of omega MF itself, and the other involves the rate of change of RPA with respect to F. From here, I come to this point. The first term, d dt of omega mf with respect to f, is nothing but the angular acceleration of omega with respect to f. This term is angular acceleration of omega of m with respect to f, and of course cross with RPA. Whereas the second term, what you see here, I have just kept it as before at this point. I call this equation number 4. Now I am going to process this second term of 4 even more, even further. I am going to process it. I am going to write d dt of RPF using intermediate frame m. So that becomes d dt of RPAM plus omega mf cross RPA. Here I am again using the same relationship that we have here. This is what is being used there also. After having split this term into two terms, I am going to put it back in 4, and then this equation, what you see here, is written in its full form, d dt omega mf cross RPAF. This is the term that is same as before on the left hand side, but on the right hand side I get first this term, which I have already processed, and then I bring in this term omega mf crossed with d dt of RPAF, which I am going to get from this equation. Okay, I'm going to get from this equation. Now here you see VPM appearing, but VPM is nothing but this. We have done this replacement already once. So this has been replaced by VPM, and then the other term comes here, and that is the cross product. The whole thing has to be crossed with omega mf. So what do we get? So simplifying it a little bit, I get the angular acceleration crossed with RPA, which is same as this term, plus omega mf cross VPM, which is coming from here, and then a double cross product, omega mf cross omega mf cross RPA. Okay. So now tracing back to the tracing our steps, all our steps back to where we started with, we started here, right? We started here, APF. I am putting that APF here. The first term became AF, that AF has come here, and then this whole term we have worked hard on this term, and that this whole term is actually appearing here. So I get an angular acceleration term, I get a double cross product term, and then I get omega mf cross Vpm 2 times. Why do I get it 2 times? I get it 2 times. First contribution comes from here itself, which I am putting here, and then the other contribution is coming from this term here, ddt of Vpmf. When we process that, we had another omega mf crossed with Vpm that is being added together. So now we get 2 times omega mf cross Vpm and of course APM here. So it is a very busy slide. I agree. Lot of processing is happening. I agree. We go back and forth trying to simplify things, substituting one thing by another. But after the dust settles down, after we follow the methodology presented here and the dust settles down, you do get a relationship between APF and APM with 4 extra terms on the right hand side, and indeed that is what the acceleration transfer relationship is. So this one slide itself presents the full proof of this relationship. Now, having made ourselves familiar with the velocity transfer and the acceleration transfer relationship, and also having completed the mathematical proofs of these two relationships, let us consider a special case. A special case in which the velocity transfer relationship and the acceleration transfer relationship simplify to a certain extent. That special case is when P is fixed in M. Recall that when I derived the two relationships on the previous slide, I was saying that P was a freely moving point in space. It was a freely moving point in space. But now I consider a case when P is a point fixed in it. So of course it will not look like this, but maybe I should draw P here, something like this. So the diagram can be adapted. But the adaptation of the diagram is not the main focus of this slide. I want to look at the expressions themselves and see what terms can be dropped from these two relationships. So this is the velocity transfer relationship in its full glory for any particle P in general. But if P is fixed in M, then Vpm is got to be 0. If P is fixed in M, then for an observer who is tied to M, P is going nowhere. Velocity of P with respect to M is 0, and thus this term will drop out, simplifying the velocity transfer relationship to this form. So while applying these equations, while trying to solve some problems using these relationships, if we are aware that P is a point fixed in M, you don't have to carry along this extra term. This can be dropped. Coming to the acceleration transfer relationship, the fact that P is fixed in M will take away two terms from the equation. What are those two terms? The first term is APM, that will vanish. Why? Because APM must be 0 if P is fixed in M. If P is fixed in M, the particle P is going nowhere with respect to the frame M, with respect to the observer tied to frame M. The particle will have 0 velocity, which we have acknowledged already. It will also have acceleration 0. APM will also be 0. So APM 0 takes away this term. BPM 0 takes away this term. We are left only with 1, 2 and 3 terms in the acceleration transfer relationship, and that simplified form I have written at the bottom of this slide. As I said earlier, in problems where P is a point fixed in M, we can just use these two equations directly without bothering about BPM and APM. Now let's go ahead and try to solve a problem. Solve a problem where the velocity transfer relationship and the acceleration transfer relationship will be used. Moreover, the relationship between angular velocities of different frames in context and the angular accelerations of different frames in context will also be applied here. This example will serve as a good illustration of the concepts and theories that we have built so far. This problem is from the book Baer and Johnston. Let's read the problem statement and try to understand what is going on here. The problem statement says that in the position shown, the thin rod moves at a constant speed 0.1 meter per second out of the tube BC. Where is that thin rod? This thin rod is here. This is the thin rod they are talking about. Where the point A moves at a constant speed out of the tube BC. Where is BC? This is BC rod. At the same time, tube BC rotates at a constant rate. Tube BC rotates at a constant rate with respect to arm CD. This purple color RB is arm CD. Knowing that CD rotates about the x-axis at the constant rate 1 radian per second, CD is rotating with respect to ground at a constant rate of 1 radian per second, find velocity and acceleration of A with respect to ground. So we need to find the velocity of this point with respect to ground and acceleration of A with respect to ground. Now where is the ground? Now this rod, this grey rod, can be considered as the extension of the ground itself, and I am calling that as RB1. So G can also be called, G is same as RB1, rigid body 1. How many more rigid bodies we have? So this is rigid body 1, This purple color thing I am calling as rigid body 2, then the red color tube I am calling as rigid body 3, and finally we have this thin rod which I am calling as rigid body 4. So in this problem there are 4 rigid bodies. In other words, we can say there are 4 reference frames. And we need to find the velocity and acceleration of this point with respect to RB1. So instead of G, I can as well say that we need to find VA1 and AA1. These are the quantities we need to find. Now, if an observer is tied to RB1 and he observes the motion of A, he would see a complicated three-dimensional curve that A executes. The trajectory of A as seen by this man will be a complicated three-dimensional curve. Hard to visualize. And when it is hard to visualize, it will be harder to actually try to find VA1 and AA1 directly with respect to 1. In one go, in one stroke, it is very difficult to find. And this is where the concepts that we have built so far are going to be useful. We will use the idea of intermediate frame and intermediate point, and then we will use velocity transfer relationship and the acceleration transfer relationship to ascertain these quantities of interest. Before we do that, let us first translate the given information in text. What is given here, let's translate them in terms of mathematical expressions. Those mathematical expressions will use our own notation, the notations that we have adopted in this course. So let's reread the problem statement and keep writing the relevant mathematical quantity which we can infer from the given information. All these things are already written on this slide, but I would like to explain which part of this statement is giving which of the quantities here. Let's reread the statement. In the position shown, the point A moves at a constant speed out of the tube BC. Now this statement effectively means that VA3, look at the diagram here, A is the point of interest, 3 is this body tube, VA3 is 0.1 meter per second in the J direction. So this is the J direction. This is the J direction. That's what I have written. VA3 is 0.1 meters per second along the J direction. Next statement. At the same time, tube BC rotates at the constant rate of 2 radian per second with respect to arm CD. With respect to arm CD. So BC rotates at a given rate with respect to arm CD. So that should be omega 3 bar 2, omega 3 with respect to 2. So this number 2 radian per second should be 2 omega 3 2. And then the direction we infer by the arrows that have been shown on the figure. So this particular arrow is denoting the angular velocity of RB3 with respect to RB2. And that direction is plus k, and that is what I am putting here, plus k. Further, it says that the tube BC rotates at the constant rate. It means that omega dot 32 will be 0. If the observer is sitting on this purple tube, purple RB, and he observes the motion of the red RB. The red RB rotates with the angular velocity which is constant. So for him, for this man, the angular velocity magnitude is constant, that is 2 radians per second, and then mind you, the direction of omega 32 as seen by this man always remains the same, always remains the same. For this man sitting on RB2, omega 32 is always pointing in this direction along the purple tube itself. So for him, omega 32 magnitude doesn't change, it remains the same as 2 radian per second, and its direction also remains the same, that is along the purple tube itself. And that is why I am saying that omega 32 must also be 0. Moving on, next statement, knowing that CD rotates about the x-axis again at a constant rate. So CD is rotating about the x-axis, CD is rotating, the RB2 is rotating at a constant rate. Rotating with respect to what? Now this part, this detail is not given in this problem statement. However, if I am the author of this problem, I would like to write this extra phrase to make it very clear that rod CD rotates about the x-axis at a constant rate with respect to ground, which means that omega 21, look at this, this is RB2, this is RB1, omega 21 is 1 radian per second along the I direction, and that I know because of this arrow given here. Furthermore, since this angular velocity, this is a constant rate, it says it is at a constant rate, I infer the following. If I am an observer sitting on this rod, the purple RB or RB2 rotates with a constant, the angular velocity of the purple rod with respect to this man has constant magnitude, and that magnitude is 1 radian per second. And further, the direction of the angular velocity of 2 as seen by this man never changes. It is always along this direction. Direction is always along RB1, and the magnitude is constant at 1 radian per second, and that makes me conclude that omega dot 21 must be 0. I have another piece of information. And then I missed this part. I should have inferred this with the first statement here itself, but still not too late. I go back to the first statement and it says the thin rod moves at a constant speed 0.1 meter per second, right? Constant speed 0.1 meter per second. So 0.1 meter per second, and this doesn't change. It means VA3 is 0.1 meter per second and it doesn't change. That implies AA3 must be 0. So these 2-3 sentences that the author has put here helps me identify these quantities, the numerical value and their direction and the directions of these quantities, and these will be helpful to us once I start using velocity transfer and acceleration transfer relationship to get the primary quantities of interest, which are VA1 and AA1. Let's talk about VA1 first. It's always a good idea to start with velocity, and once velocity has been found of a particle of interest, if required, you can go ahead and try to find the acceleration of that particle also. So I am going to use the concept of IF and IP In other words, I'm going to use the velocity and acceleration transfer relationships to find VA1. I choose my intermediate frame as a frame with respect to which the velocity of A is known or geometrically very simple. This is the guideline we should follow to identify the intermediate frame which will be used to find this quantity. I repeat, IF should be a frame with respect to which velocity of A is known or geometrically very simple. Which body here is such that with respect to that body, velocity of A is either known or it is geometrically very simple to visualize. Clearly, that body is RB3. If you sit on RB3, if you tie yourself to RB3, velocity of A is known, and that we identified on the last slide itself. VA3 is simply U times J. So I will choose 3 as my IF, intermediate frame, before I apply the velocity transfer relationship. But then, having chosen an IF, I should also choose an IP, intermediate point, so that I can utilize the velocity transfer relationship that we derived earlier. And to remind you of what I am talking about, what IF and IP I am talking about, let me go here and show you. See, I was saying that I want to find VPF. I want to find VPF, and I am using M as an intermediate frame such that VPF can be found in terms of VPM. So I need an intermediate frame. This is my intermediate frame. But then I also need an intermediate point. This is my intermediate point. An intermediate point must be fixed in intermediate frame. That's what is happening here. So this is my intermediate frame and this point is my intermediate point. These two items, an intermediate frame and intermediate point, is enabling me to write VPF in terms of VPM. Same thing will happen for acceleration transfer relationship. You are trying to write APF in terms of APM, and for that you need an intermediate frame, M. M is the intermediate frame, and you need an IP, intermediate point, which is appearing here. Okay? So in that problem, currently my quest is to identify an appropriate IF and appropriate IP to proceed further, take the next step. So IF is frame number 3 and IP I am choosing as point C. It is always a good idea to choose the IP as a point of intersection, as the point of intersection of the IF that you have already chosen and the next RB that is attached to the body. So this IF I have already chosen. I am saying it's a good idea to choose IP as a point which is at the intersection of your IF and the next body in context. And that gives me, that leads me to choose C as my intermediate point. And do remember, any time you choose in the an intermediate point, make sure that C is fixed in your IF. Has to be. So RB3 as IF and C as IP are legitimate choices with the help of which I am going to write the velocity transfer relationship in this manner. Okay. Now remember, we are using this relationship in the background. This is what I derived. The freely moving particle was P. The main frame of interest was F. M was the intermediate frame, A was the intermediate point. This is the form in which we derived the relationship. However, in this problem, you will have to do some adaptations and do those adaptations rather carefully. What are those adaptations? So you will refer to this formula, but keep in mind that in this case, in this problem, this P has to be A, because A is the point of interest, freely moving particle in space. So you need to change carefully all P's to A. All P's should be carefully changed to A. And the A that is there in this formula has to be carefully changed to the newly chosen IP, which in this case is C. Right? So you change this P to A, this P to A, this P to A, and then you change this A to C, this A to C. And then this M what is appearing here, that should be changed to 3 in our problem. And then the F that is appearing here, that is 1. Okay, all these things I have written here for clarity. So this kind of substitution needs to be done, or adaptation needs to be done very carefully. And when you do all those steps carefully, in this context, coming back to this problem, you can write VA1 as VC1 plus omega 3 1 cross RAC plus VA3. This is the expression we have. Now, it is a good idea to start from the right hand side of this equation and see what are the known terms and what are the unknown terms. The terms which are known, you don't have to do anything more. You can go ahead and do the calculations, but the terms which are unknowns, you will have to perform some extra steps. So let's inspect what is the status of all these terms in right now, whether we know them or we don't know them. The first term is VA3. I am claiming that to be known because on the last slide, when I was translating the problem statement, into these expressions here, I did get VA3 as 0.1 meter per second along the J direction. So that's why I call this quantity VA3 appearing here to be a known quantity. K means known quantity. So VA3 is known. Then I move to the next term, RAC. You look at the figure. RAC. Do we know RAC? This is RAC. This vector is RAC. Do we know? Yes, we know. It is 0.3 meters along J direction. That's what I have written here. So this is also known. I mark it as K. I move to the next quantity here, which is omega 3 1. Now omega 3 1 is currently unknown. It's not known. Again, if you go back to the previous slide and you see this list of items that we identified, based on the problem statement here, I do not have omega 3 1. I have omega 3 2, I have omega 2 1, but omega of 3 with respect to this man being tied to 1 is unknown right now. Right now it is unknown, but is there a way to find omega 3 1 based on the information that is already available to us? Indeed, it is possible. The way I am going to find omega 3 1 is invoking this relationship omega 3 1 equals omega 3 2 plus omega 2 1. And now pay attention to this. Omega 2 1 and omega 3 2, these quantities are indeed known from our table that we created here. I have omega 32 and omega 21 appearing directly from the problem statement, the statement of the problem given to us. So if I know omega 32 and I know omega 21, indeed omega 31 now becomes a known quantity, and that is why I have marked here, now it is K. K means known quantity. Now moving along this direction, this is known, this is known, this is known. Now we come to this VC1. Is it a known quantity? No, it is not a known quantity. Right now it is not a known quantity. On the previous slide, if you go back, you will see that omega 31 VC1 is not known. So we need to find VC1. How do we find VC1? So VC1 is velocity of this point with respect to this man. Now to find VC1, I am again going to invoke the idea of intermediate frame and intermediate point. I'm going to invoke one more time the idea of intermediate frame and intermediate point. So this is the point I want to find VC1. I am going to say that let's use RB2 as IF. Why do I say RB2 as IF? I am following the same guideline what I mentioned earlier. You should choose IF to be that reference frame or that body from where the motion of the point of interest is either known or it is geometrically very simple. In this case, you can see that if you choose RB2 as your IF, VC2 is actually 0. Indeed, it is known. And that is why I would choose RB2 as IF. Once I have chosen an IF, I need to choose also an IP, and the IP should be part of RB2. Now what was the guideline I mentioned on the previous slide, how to find an IP? I said that try to choose IP to be a point which lies on the intersection of the IF and the RB next to it. And that point indeed in this case is D. So I am choosing D as my IP and then going to write velocity transfer relationship such that VC1 is written as VD1 plus omega 21. 2 is the IF. Remember, 2 is the IF cross RCD. This is the IP. This point is the IP plus VC2. But VC2 is already 0. Doesn't matter. RCD, do we know RCD? You look at RCD. Where is RCD? This is the vector RCD. Indeed, it is known. It is 0.5 meters along the K direction. That's what I have written. So this is also known. Omega 21 is indeed known. You go to the first slide when I started the problem. This information about omega 21 came directly from the problem statement. 1 radian per second along I. So this is known. Next term is VD1. Is it known? Indeed, it is known. You look at VD. VD with respect to 1 is actually 0. D is not going anywhere as seen through the eyes of the man who is sitting on I. Okay. So in this equation, everything is known. VC1 you can find. And once you find VC1, we go back to the previous slide. We go back to the previous slide with VC1 known from the next slide. This now from the next slide, this becomes known also, and thus we are now in a position to find VA1. and if you put all the numbers, it turns out that VA1 is this much quantity.